Good day, everyone. We are from the Department of Statistics of the CUHK. I would like to welcome you all to our presentation on differentiation rules. To begin with, let's take a look at our agenda for today. We will start with an introduction, followed by discussions on the constant and power rules, linearity of differentiation, and then move on to the product and quotient rules. As we all know, computing derivatives by the first principle can often be a tedious and time-consuming process. However, there are general rules that we can apply to find the derivative of an elementary function in a more efficient manner. In this presentation, we will explore these rules and their respective proofs and applications. Now, let's dive into the constant rule. Theorem 2.1 states that the derivative of a constant is 0. In other words, if we have a constant c, its derivative is equal to 0. This rule may seem simple, but it provides a solid foundation for the more complex rules that we will be discussing later on. This can be proven by letting f of x equals c, where c and x are both real numbers. By applying the definition of a derivative, we can see that f prime of x equals the limit as h approaches 0 of c minus c, divided by h, which equals the limit as h approaches 0 of 0 divided by h, which equals the limit as h approaches 0 of 0, which equals 0. Next, we have the power rule. Theorem 2.2 states that for each positive integer n, the derivative of x raised to the power n is equal to n times x raised to the power n minus 1. This rule can be useful in finding the derivatives of polynomial functions and other functions involving exponents. This can be proven by letting f of x equals x to the power n and applying the definition of a derivative. By expanding using binomial theorem and simplifying, we can see that f prime of x equals n times x to the power n minus 1. Theorem 2.3 extends the power rule for any fixed exponent n where both x to the power n and x to the power n minus 1 are defined. Similarly, the proof involves using exponential functions and limits. Note that we have used two special limits as shown on screen. Now let's move on to linearity of differentiation. Theorem 3.1 states that for any functions f and g and any real numbers, a and b, the derivative of the function h of x equals a times f of x plus b times g of x with respect to x is h prime of x equals a times f prime of x plus b times g prime of x. In other words, the derivative of any linear combination of functions equals the same linear combination of the derivatives of the functions. This theorem encapsulates in a single rule two simpler rules of differentiation, the sum rule and the constant factor rule. By applying this rule, we can easily find the derivative of polynomial functions and other linear combinations of functions. This theorem can be proven by letting j of x equals a times f of x plus b times g of x, applying the definition of a derivative, rearranging terms, factorizing out a and b, and using the fact that f and g are differentiable. As an example, these rules are all we need to differentiate any polynomial p of x equals a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1 plus a so plus a sub 1 times x plus a sub 0. We differentiate it term by term, using the sum rule, use the power rule on each term. For each monomial, using the constant factor rule to bring along constants. We can refer to the example on the screen to understand how it works. Next on our agenda are the product and quotient rules. These rules are worthy of proof as they aren't what you would expect. Therefore, you are advised to memorize them. Theorem 4.1 is known as the product rule. It states that for functions f and g, the derivative of their product h of x equals f prime of x times g of x plus f of x times g prime of x with respect to x. This rule may be extended or generalized to products of 3 or more functions or higher order derivatives of a product. Discovery of this rule is credited to Gottfried Leibniz, who demonstrated it using differentials. The rule for integration by parts is derived from the product rule, as is a weak version of the quotient rule. The proof involves applying the definition of a derivative to h of x, rearranging terms, and using the fact that differentiable functions are continuous. Note that the limit as delta x approaches 0 of g of x plus delta x equals g of x is deduced from the theorem differentiable functions are continuous. Let's take a look at some examples to see how the product rule can be applied. Suppose we want to find the derivative of the quantity x squared plus 3x minus 2 multiplied by the quantity 3x to the fourth plus x squared minus 1. Using the product rule, we can differentiate it term by term and use the power rule on each term. The derivative would be the quantity 2x plus 3 multiplied by the quantity 3x to the fourth plus x squared minus 1 plus the quantity x squared plus 3x minus 2 multiplied by the quantity 12x cubed plus 2 times. Here's another example. Suppose we want to find the derivative of the quantity x squared plus 1 multiplied by the quantity x cubed minus 2x multiplied by the quantity 3x to the fourth plus 2x squared plus 2. Using the product rule, we would have a new term for each factor, each one with one of the factors differentiated. The derivative would be rather complicated, as shown on screen. Let's have some notes on the product rule. The rule can be extended to products of 3 or more functions. For example, for functions f of x, g of x, and h of x, their product f of x times g of x times h of x is a derivative equal to f prime of x times g of x times h of x plus f of x times g prime of x times h of x plus f of x times g of x times h prime of x. This also works for products of more factors, where you have a new term for each factor with one of the factors differentiated. Finally, Theorem 4.2 is known as the quotient rule. It states that for functions f and g where g of x is not equal to 0, the derivative of their quotient h of x equals f prime of x times g of x minus f of x times g prime of x divided by the quantity g of x squared with respect to x. This rule can be useful in finding the derivatives of functions involving fractions, or ratios. Again, the proof involves applying the definition of a derivative to h of x, rearranging terms, and simplifying. As an example, let's find the derivative of f of x equals the quantity x squared plus 2 divided by the quantity x squared plus 3x plus 3. By applying the quotient rule and simplifying, we can see that f prime of x equals the quantity 2x times the quantity x squared plus 3x plus 3 minus the quantity 2x plus 3 multiplied by the quantity x squared plus 2 divided by the quantity x squared plus 3x plus 3 squared. In conclusion, we have discussed several differentiation rules including the constant rule, power rule, linearity of differentiation, product rule, and quotient rule. These rules provide us with a more efficient way to compute derivatives without having to rely on first principles. Thank you for listening to my presentation on differentiation rules. I hope you found it informative and engaging.